Earthquakes produce two types of seismic waves: body waves, which can travel through the Earth, and surface waves, which only exist at the interface between two materials with very different physical properties. In the case of the Earth, the surface waves travel on the Earth's surface between the rock and sediment and the atmosphere. There are two types of body waves: P waves and S waves. This is a P wave. The P wave is the primary wave because it travels fastest and arrives first at a recording station. It's a compressional wave in which propagation occurs via alternate compression and dilation in the direction of wave movement. If you study the animations carefully, you will see that points move alternately forward and backwards. This movement is the result of compression and then expansion, and thus depends on the medium having compressive elasticity. The other type of body wave is the secondary, or S wave. It's called the secondary wave because it travels slower than the P wave and therefore arrives later at a recording station. You can also think of the S as referring to shear, because that's the way in which the S wave propagates, as alternating shear in a direction perpendicular to the direction of wave movement. You can see the little black box in the upper animation undergo shear deformation as the wave passes by. The animation in the lower left shows how points in a body move as an S wave passes by. Notice that they move up and down while the wave moves from left to right. This up-down movement produces a shear stress which restores the point to its original position. Surface waves deform the surface of the Earth, but just like ocean waves, which are another form of surface wave, they also deform the Earth a short distance away from the actual interface. There are two main types of surface waves: Rayleigh waves and Love waves. The Rayleigh wave looks like an ocean wave. The surface of the Earth rolls up and down as the wave passes. Notice the little blue arrow that shows the direction in which the surface sort of rolls backward as the wave passes. In this animation, you can see how the ground moves in a circular motion against the direction of the wave movement. The audio on this animation, taken from YouTube, isn't very good, but the animation does a great job of showing how the ground moves when a Rayleigh wave passes by. It's no wonder that Rayleigh waves cause such damage to structures that aren't built to withstand these kinds of forces.
As Rayleigh waves travel in backward rotating circles, they cause the ground to accelerate through a vertical lift, a horizontal push, a vertical drop, and a horizontal push in the opposite direction.
The other type of surface wave is called a Love wave. Love waves produce surface motions that are entirely horizontal, side to side, as the wave propagates. This side to side horizontal motion is a little difficult to see in some animations, but if you study it carefully, you will see that the ground isn't actually moving up and down, just side to side, as indicated by the pink arrows. Here's another animation of the Love wave. And here's another one showing the wave coming right at you. In this animation, you can see how the wave causes the ground to shift sideways but not vertically. Love waves are also very damaging to structures which aren't designed to withstand this kind of twisting motion. P waves are the fastest waves, followed by S waves and then surface waves. In general, the velocity of all seismic waves increases with depth into the Earth until they hit the liquid outer core, at which point the velocity decreases. I should have said all body waves, of course, because surface waves don't travel through the Earth. The S wave velocity actually drops to 0 at the outer core boundary because the liquid in the outer core has no shear strength and thus can't support the passage of S waves at all. Because the velocity of body waves increases with depth, waves refract or bend as they enter the Earth. This bending causes waves that enter the Earth at an angle to bend and eventually emerge from the Earth following a curved path, like shown by the red and green arrows on this diagram.